more students to come, but they will come with the possibility. Okay. So, welcome again to this third seminar in Horizon in Engineering. Today, the talk will be held by Dr. Shumin Zhai. Dr. Shumin Zhai is a researcher at Google. He has been chief responsible for different projects, between which also the Pixel, right? And today he will talk about us how to use better communication ways between smartphones and users. So I would like to thank Dr. Zhai for his gentle adhesion to these seminars and give the words to him for this lesson. Thank you.
Thank you. Thank you very much for inviting me. I'll talk about a line of work my colleagues and I have been pursuing for a long time, since the beginning of 2000, or even 1999. Actually, some of the foundational work was even earlier than that. It's a product of many, many people. In that sense, I'm just a spokesperson. There are many colleagues, interns, postdocs have worked on this project that I started back at IBM Research. And about 7 years ago, I joined Google, and I continued at Google to work on more efficient ways of entering text on mobile phones. Why mobile phones? Because because of the so-called mobile revolution. That's one of the biggest shakeups in the field of computing. There are estimated more than, I think, just Android alone, there's 2.5 billion users, active users, or more. I'm showing two charts that shows the importance and the profound change that mobile phones, smartphones has brought to the society. One is the amount of, this is cell phone sold every year. But a very interesting chart, this was recently published, was that the sales of gums that declined dramatically for reasons that is people actually pay attention to their phones when at the grocery store or supermarket checkout. So that's where usually people buy gums. But now they're looking at the mobile phones, didn't pay attention to the stands. So the gum sales went down dramatically since the introduction of the smartphones. It just shows that how much mobile phones, particularly smartphones, have changed the society. Why so? What made the mobile revolution to work? Many, many reasons. Number one is the progress in hardware technologies, including input sensing technologies, display technologies, and so on and so forth. This was when I was young, working on my PhD in virtual reality areas and telerobotics and so on. In order to program my PhD research, I had to have a high-end SGI workstation, which costed about $200,000 in 1993. 20 years later, this mid-ranged smartphone Nexus 5 costed like 3 orders of magnitude less. I bought a phone like that because I worked on it too, and I sent it to my PhD advisor, telling him I've repaid all the computing power he invested in that workstation. If you look at the Wikipedia page for this phone and that workstation, on all aspects in terms of display density, CPU, speed, amount of memory, everything is higher specs on this mobile phone. That's the number one reason that we could do so much more. But there's also a lot of UI design work and software development, a lot of creativity, and a lot of human factors or scientific-based principles that went to UI design that helped. And I'm going to illustrate some of that. And increasingly, it's also machine intelligence. There's just a lot more data that can be abstracted, packaged, modeled into predictions that can help user interaction. Of course, search has always been an important part of mobile experience, and search itself has always been based on machine intelligence of some sort. And increasingly, they're moving into deep learning as well. My own interest in the past 20 years had been mostly focused on text input. And why text input? This cartoon illustrates one way of thinking about writing. This was actually in the last wave of mobile technologies in the PDA days. This is about also by now 20 years ago. Oh no, less than 20, maybe since it was 2000-ish. The idea is that the importance of written communication has always been important to human activities and civilization to some degree. So we start out by, of course, almost by definition, civilization started by carving symbols on stones, on tablets, and moved later on to writing on paper or printing on paper. The Industrial Revolution brought us the typewriter, which was around 1860s. And then we moved to computer information, IT technology era, where emails and web and so on and so forth enabled us to do a lot more communications. And now, even the last era, we moved to PDAs. We raised this question how we can, again, carve symbols on tablets, but obviously it has to be in a much more efficient way. Text input is very interesting from a research point of view because fundamentally, text input is a method of coding. It's a method of encoding and decoding. The encoding part is something of a human input, a human gesture, and that has to be encoded. That's encoding information. So either language or gesture or written form, it's all encoding some sort of information, meaning. And that information has to be decoded by the system, except this design has to be in such a way that it's efficient for the human user. That is either easy to learn or memorable or efficient. And efficiency is defined by human communication. And there's many ways you can think of doing this. Almost infinite number of ways to do text input. And here's an example that I hope the video works.
The tech world is buzzing over Apple's latest must-have gadget, the MacBook Wheel, a revolutionary new laptop that does away with the keyboard. Tech Trends reporter Jeff Tate has more.
Thanks, Andrea. Say goodbye to the keyboard and hello to the future of laptop computers. With the MacBook Wheel, Apple has replaced the traditional keyboard with a sleek, touch-sensitive click wheel. Apple CEO Steve Jobs introduced the product yesterday at the annual Mac Expo. Senior product innovator Brian Gilman says the MacBook Wheel will make typing a thing of the past.
At Apple, our philosophy is create products that are simple to use, and nothing's more simple than a single giant button.
Gilman showed me how the revolutionary new computer works.
Just open the Intuitype alphabet menu here, scroll to the letter you need, see? And center click to select it. Then click again to capitalize, and repeat this process for each new letter. It couldn't be simpler.
Huh.
You can also let the predictive sentence technology complete the sentence for you.
Gilman says the MacBook Wheel has also simplified the organization of files, so searching your hard drive will be a snap.
Just press both sides of the wheel concurrently and center click in there. You have an alphabetical listing of every file on your hard drive. Everything is just a few hundred clicks away.
Apple is calling the MacBook Wheel the most intuitive product ever designed.
Here at Apple, we like to think that we're giving customers features they don't even realize they want yet.
While the MacBook Wheel won't hit the shelves for another 3 to 15 months, many Apple users already have it on their wish list.
I'll buy almost anything that's shiny and made by Apple.
Alex Zalman was one of the
So of course, that's a parody. It's a hypothetical way of doing text input, but it just shows there are many ways you can invent a way of writing text. It's a matter of efficiency, whether it can be adopted. And there's actually many dimensions to the goodness of a text input method. Okay, here, let me go.
The lucky few to get to try out a Mac wheel and spent 45.
Okay. How do I? That looks right. More or less right. Okay. To do text input right, I've personally felt, and many people felt, not necessarily agreed by everyone, is that we have to understand the underlying mechanism in terms of human performance, in terms of human factors. So the field that I specialize in is called human-computer interaction. The idea is to understand the limitations and regularities and capabilities of the human user and translate that to user interface design. And this tradition started by some of the pioneers in the field, in particular Card, Moran, and Newell, that wrote the book called The Psychology of Human-Computer Interaction. And they draw inspiration from a fairly old piece of knowledge called Fitch's Law that was published in 1950s. That was shortly after Shannon's information theory. And that was one way to understand human behavior and human performance. Basically, Fitch's Law says that human movement is in some sense determined by information. That is, the amount of information you express in every single reaching movement is to a very large extent determined by the amount of information you want to express. And that reflects at a very simple formula, that is the distance you travel and the target, the size of the target you want to reach. And that ratio take a log form, which happens to be in the unit of bits, is the important determinant to movement time by this equation. And this works in many, many forms. You can use a stylus or finger or underwater, inverse ways. It all follows so-called Fitch's Law. And that's one piece of regularity or phenomenon that had been discovered a long time ago. And that's one of the main pieces of kind of cornerstone that HCI researchers try to apply to design user interfaces. But this is an example of how it's used. So for example, when we moved to virtual keyboard, where at the time it's mostly traveling using a stylus to travel on a virtual keyboard. So imagine you move you tap one key at a time with a stylus. And on average, how long does it take, how much distance does it take to travel to the next key? And the answer is about 3.5 letters on QWERTY for English. For Italian or other languages, it's actually quite similar. They're all quite long. There are fundamental reasons to that, and there's a lot of folklore theories explaining why. One of the explanations is that the QWERTY keyboard was designed to slow people down. That's not quite right, because the inventors of the QWERTY design had no idea how people were going to type at the time. The very recommended way of typing today, namely touch typing, wasn't discovered till some 20, 30 years later. But it was mostly designed to minimize mechanical jamming. So the initial typewriter prototypes gets jammed very easily. The two hammers that's supporting, or the lever supporting the keys that would come too close to each other. So therefore, they spend a lot of time trying to put the keys, the likely diagrams or two consecutive letters, to be on the opposite side of the keyboard. So you hit one hammer on one side and hit the next hammer likely to be on the other side. Therefore, it doesn't gets jammed. Was the primary reason for that. But as a result of it, it's actually pretty good for two-handed typing. But when you use a single stylus or single finger to travel on keyboard, it gets pretty difficult because it moves back and forth over a greater distance at a higher frequency than necessary. So let's say we're allowed to optimize for that. How to do that? And this is where Fitts law comes in. That is, we first of all define an energy function or object function. The energy function in here is what I call the Fitts digraph energy, meaning, first of all, you can use Fitts law to model the time it takes from one key to another, which is, again, taking a log form of the distance to key size ratio. And that take a log form that become the time. And then if this time get multiplied or weighted by the transitional frequency from one letter to another, which you can learn from any corpus of text, then you can compute an average distance or average time to type a letter on a keyboard. And using that energy function, we can drive the optimization process of the keyboard to the minimum energy state. And the most classic method of doing that is called simulated annealing. Some of you may know about it. But if you don't, think of the keyboard as a molecule, each key as an atom, and where do the atoms want to stay? That depends on the temperature of the system. In high temperature, atoms tend to bounce around, but when you get to lower energy state, they tend to be frozen. And if you raise the temperature up and down, they eventually all find the most stable place to stay, which is the lowest energy state. You do this by essentially swapping letter pairs or randomly moving the keys. But if you make a move or swap a pair, if the energy goes down, you take it by intuition. But the trick is that when the energy goes up, you also take it sometimes. And that magic probability follows a so-called Boltzmann function. And that will guide you sometimes, only by sometimes taking worse off moves, you will be able to get to the global minimum rather than get stuck in a local minimum. So that's the basic thought of simulated annealing as applied to here. And that's why we call this keyboard atomic keyboard. It happens to stands for some acronym, but the idea is that it's the atom movement that guided themselves to optimal state. Also, interestingly, we can do this. So one question that comes up is that if you do this for English, wouldn't that mean it's get optimized for English, but not for other languages? Maybe it's worse for other languages. So we did some experiments later on by testing whether we can optimize for multiple languages at the same time. And we come to realize each time you find a minimum energy state, it's a configuration that is not necessarily unique. So if you do this minimum energy minimization again, you may end up another layout that is similar in energy state in the objective function, but very different configurations. Sometimes slightly different, sometimes quite different. So that means the energy landscape has a fairly flat valley floor. And we took advantage of that to accommodate other design dimensions. One design dimension is, in this layout, we made it alphabetical. So if you see ABCs tend to be in one corner, in this ABCD, and XYZ tend to be in the other corner. So to give a user a clue when it comes to learn a new layout. We also use the same idea to accommodate multiple languages. So if we put so-called fixed P, that is other than English, French, Italian, German, Portuguese, Spanish, plus Chinese, and we come to find that we can still minimize the energy or the travel distance, which is quite equivalent to about 1.5 keys-ish rather than 3.5 keys, almost simultaneously for all languages, which is quite interesting. Partly because almost all languages, when it comes to phonology at this level, have a great deal of similarity because they all tend to be alternating between vowels and consonant, for example. So there's enough commonality to accommodate the multi-object function minimization. But this work, nonetheless wasn't quite enough because traveling with a single stylus quickly become obsolete. Rather, most of the world moved to touch screens. So we had to move on to learn more about human behavior to try to leverage better, try to leverage new phenomena as applied to keyboard design or other UI design aspects of human-computer interaction. So this is another type of phenomena we discovered that is we call the law of crossing. If you say Fitch's law is law of pointing, we want to invent a new vocabulary that is based on crossing a graphical object in different ways. So you move in one direction or vertically or horizontally or different directions or back and forth. With that, we found that it also more or less follows Fitch's law. So if you say, I cross this letter, this bar, this way, here, and then jump to the other side and cross there, or there are sets of these that cross continuously, it's all actually more or less follow Fitch's law, except they have a different slope. So we can design tasks according to, design UIs according to what each modality is better at. And later on, we also move this thought to something more different. That is, if you follow a trajectory within a constraint, and that is a continuous constraint on movement rather than a point constraint or target constraint. And that also follows a new relationship. We call it law of steering. And this was all done quite in the late 90s. So with all that knowledge, we found that it was still not enough to invent a new method for text input because we also needed to understand the cognitive memory aspects of human performance. And there's a lot to be said about human learning and human memory. But one fairly well understood knowledge is that high performance skills, like riding a bicycle, like typing, like sports, they all tend to be well practiced but recall driven. That is, there's some sort of implicit memory or procedural memory that's already ingrained into the human body or human mind. And then it's a matter of recall. You don't actually think about it. You don't look for external references in order to accomplish that movement. And that's usually high performance, so it's recall driven. But user interfaces, since the desktop PC was more about recognition. It's more about look and hunt and click. So for example, the typical design is graphical user interfaces. Is that you click on a menu, you see what's available, and then you click again, you drill down, you use a navigation model, which tend to be quite slow. That's why for programmers, at least, it's still faster to use Unix commands like a command line language to do fast navigation rather than using mouse clicks. So can we find a way to design user interface to be starting from the recognition end and move to the recall end? And that was the goal of this project. Eventually, we called shape writing. The idea is that, let's say, we have a QWERTY keyboard, and we started with pointing the word, let's say, quick. You type Q, I, U, C, K, roughly. And then each time you do this, our system would let you realize it can be also done by a shape. And that shape is start from Q, going to U, going to I, going to C, going to K approximately. And that shape is also an encoding to the word you want to enter. And the idea is that over time, the shape will become the more dominant way of driving your interaction, and you will see less metaphorically. You don't have to pay as much attention to the keyboard, but rather more memory recall component will drive the action. This is why we call it shape writing. Initially we called it SHARC, standing for shorthand writing on stylus keyboard. And this was published in 2003. And in 2004, we made this method, scaled this method to a practical level with 10,000 words. So we call it large scale. The second paper is called large scale keyboard, large scale shape writing, or something like that. And here's the example. Here's the demonstration of that. Hopefully it's still online. You see. SHARC is a pen-based text input system. It combines a stylus keyboard with pen gesture recognition technology. The keyboard layout can be either the standard QWERTY or the atomic layout shown here that is optimized for stylus motion. For each word in a large lexicon, a shorthand symbol or a sock graph is defined by connecting the word's letters on the keyboard. For example, the word word is represented by the letter trace W-O-R-D. A novice user can look at the keyboard and trace the letters of an intended word. Here the user is writing the phrase, "The quick brown fox jumps over the lazy dog." Unlike speech recognition, error correction is relatively easy with the pen-based SHARC method. If a mistake is made, the user can select a correct choice from the unbest list embedded in a text stream editor, or delete an unwanted word from it. A new user can also use the animation feedback feature to learn soft graphs. The animation morphs the user's pen gesture to the ideal soft graph of the word the system recognizes. Over time, the user may remember the shapes of those well-practiced words and shift from visual tracing to recall-based pattern gesturing. As a result, the input speed may increase dramatically. We use a multi-channel pattern classification system to recognize the gestures drawn on the keyboard. In particular, the shape channel looks at the gesture's relative shape properties, while the location channel examines the gesture's absolute location information, such as pen up and pen down positions. Recognition scores from the two channels are dynamically integrated according to gesturing speed. The SHARC multi-channel recognition architecture offers enough flexibility and reliability to deal with thousands of words a user may need to write. SHARC's lexicon can be customized based on the individual user's past documents. One can also add new words to the lexicon easily. As a result, a user can practically write any word with SHARC. Here we demonstrate a few more sentences with Sharp. For more technical details, please see our paper in the WIST 2004 proceedings. Thank you. So notice the last two words in here were deliberately drawn that's out of the each keys. So only the shape information was taken into the recognition process. The idea is to remove the user's visual dependency on the keyboard itself. And it's the idea that's still not fully realized today. Although this paradigm later on was followed by many today, at the time we first released a version on Windows tablet back in 2004 that nobody practically used at the time because tablet wasn't really used as tablet back then. And then in 2007, when iOS started permitting third-party apps, we actually wrote this as a notepad application because iOS did not permit third-party keyboards till about 3 or 4 years ago. So this was a fully decade earlier. So we had to write it as an application to illustrate the idea. But even with as an application was selected as one of the top 11 iPhone apps by Time Magazine and many appraisal from different reviewers and users. Some said this is a revolutionized typing. It's the understatement of the year. It should be part of every touchscreen phones, except it took many more years to actually reach that goal. Today, it's practically on every phone if people want it. Many people don't know. But for example, the Google's Gboard that I worked on is both in iOS and on Android phones. There was also other companies have pursued the same vision. Most notably, Swipe and SwiftKey. And this is a Gboard actually also does Chinese, which is a very interesting dimension because Chinese doesn't really follow the same word unit as Roman languages. So it doesn't really have word explicitly. Rather, it has characters, a large character set. So the character size get combined into words. There's a more fuzzy boundary between what is a word, what is just a combination of new characters. So that's pretty much prehistory of typewriting, of shape writing. And as I said, 7 years ago, I moved to Google, and we started to rebuild this type of technologies from the ground up, more based on modern understanding of recognition and decoding. And this is a more principled way of doing that. So basically, any keyboard can be essentially viewed in such a way mathematically today, either tapping keyboard or gesturing keyboard, either based on strokes or based on single points. They all can be viewed as some sort of noisy input into a Shannon channel. And the noisy input here is a signal, let's call it S. Again, it can be sets of touch points or it can be a gesture on keyboard. And the computer's task is to translate that signal into a set of words, a set of probable words. And then the rest become a matter of search. So you search for your word space to find the best match to that signal. And that's almost the problem definition, statistically. And this is just a classic Shannon channel. And one way of solving this channel is to inverse the probability to a signal, to a model here I call it a spatial model. In the speech recognition field, it's called acoustic model. The idea is that we know for all words, for each word in a system, we know their spatial signal distribution in some way. And that can be like a neural network model, or it can be a simpler spatial model. Earlier in the project ShapeWriter, I alluded to some sort of dynamic weighting between a shape channel that's relative and a location channel, or that is more absolute, depending on where you actually draw the keyboard draw the shape on the keyboard, or relative to the key definition, only encoding shape aspects of information aspect of it. But once you have that, you can also look up given the context, what you have written, what is the probability of a set of words, the prior probability of a set of words, and that is given context word. And with these two submodels, the classic, the age-old Bayes rule or Bayes theorem will allow us to combine the two to reverse the problem back to given signal, what is the word probability. And in principle, you can interpret almost all design. The designers, engineers may not be conscious of this process, but that's essentially what they're trying to do. And sometimes it's more consciously applying such a classic model. Then the question is that what are these components? How to best construct these component models? So first, let's start with the spatial model. Again, this goes back to the science or knowledge on the human side. That is how humans move their fingers and hand given a target word. And the simple thing is, once again, going back to Fitts' law. But except Fitts' law actually doesn't apply to touch screen that well. The reason is that Fitts' law really models a relative precision as expressed in information terms. Essentially, it doesn't consider the instruments itself that has absolute error distribution. So when it comes to finger touch on a touch screen, often the target is much smaller than the finger itself. So therefore, that absolute component often dominates the element, the time that takes to enter or to tap on each word. So here we had to remodel Fitts' law to accommodate that component. We call it finger Fitts' law. This was only published about a few years ago, 4 years ago, or 5 years ago now. We call it finger Fitts' law. And with that, we will be able to model a single finger traveling problem. But humans don't use touchscreens as a Fitts' law movement always. Sometimes it's an implicit Fitts' law. In particular, it actually defies Fitts' law by allowing multiple fingers. And that is no longer a single n-effector travel problem. Rather, it has a greater degree of parallel action. So when people use two thumbs, or one finger, or one thumb, sometimes people actually hold their phone and also use the thumb on the same hand to operate a keyboard. This all gives different touch biases to the touch screen. And here the heat plots illustration on different what we call hand postures. In particular, they have these kind of distributions. If you see its errors on the keyboard, if you type with one finger, the touch points tend to be lower than the keys, than the center of the keys. If you type with two thumbs, they tend to be more shifted to the outside. There might be a reason that people still want to use their eyes to guide the action, so therefore it tends to leave some space for the eyes to see the keys for as long as possible. Maybe that's a reason. So the Gaussian distributions are all skewed in different ways or shifted in different ways with means in relation to the key position. So as a result, if we can build models, spatial models for each hand posture, we'll be able to do more precise decoding because the model is just simply more precise. And that will give us better results. Except we don't know in practice what finger they use. So one idea is that from their behavioral data, let me, okay, I put that slide later. One idea is to use behavioral data to infer whether they're typing with 2 thumbs or typing with 1 finger. And then we shift to different models. Except if the models are specialized, then you may lose precision when the user switch to like they are typing with 2 thumbs and then they hold a cup of coffee, they switch to 1 thumb, and that model become very different. And then for that moment, if you don't recognize the hand posture immediately, you'll suffer from the consequence of applying a wrong model or less precise model. So we use a back-off model, and we tried various experiments on that. I was actually not on this, maybe later on the slide deck that I moved to a different part of the deck. So in reality, we actually apply a standard model that is sum of all distributions together to treat as a generic Gaussian distribution. And with a generic Gaussian distribution, how the decoder works out from the Bayesian inference process is become fairly simple. That is, essentially the Gaussian distribution's width determined the weight between language model and the spatial model. And that can be solved analytically to translate to this language model weight relative to spatial model weight. And in practice, when you do these things, it is in log scale. So they instead of multiplying, probabilities become addition, and this addition can be simply viewed as 2 costs. One is spatial model cost, and the other is language model cost. And they can be made to be fairly efficient, almost to the maximum, so that you can decode hundreds of thousands of words plus pruning techniques to do it all in the scale of milliseconds, so they are real time. So I've spoken on the spatial model for tapping. For gesture, there's another set of signals and features you can use. And later on, I'll also return to that topic a little bit. But here, let me explain what is a language model. A language model, the simplest form is just a set of n-grams, meaning like if I say a word, I say how are, and you know the probability followed, the probability of you following how are is, let's say, 30%. It's a very high probability. And it could be how are things, or how are you doing, or how, there's many probability, possible candidates would have different probabilities. But the point is that it can be modeled by the preceding words. When the preceding words doesn't exist and it backs off to a lower span single word, for example, all the way to the word itself, unigram. And there's principled ways of doing that that can work out. An important part of this process of telling, also training these n-gram models is finding the right corpus. The right corpus that reflects language corpus or text corpus that reflects how the end users actually would communicate. So domain matching becomes very, very important, and finding the right language corpus is a big part of engineering. And so often the domain don't match all that well, plus any corpus will be words that you don't want to predict, such as profanity or racial bias, and so on and so forth. So filtering that is another part of the task of training language models. Of course, the model size matters a great deal. In speech recognition or other technologies, often they do decoding on the server. They can afford a much larger language model than keyboard can afford. Keyboard usually has to be on device and has to be real time. It has to be, therefore, it can only afford a relatively small language model. And there's also a great deal of privacy and personalization issues that goes with language model training. So here's one experiment to test how strong a language model effect will have. And by the way, when I say language model, essentially it's synonymous with decoding, because without language model prior, you really cannot do decoding at all. But the language model can be as simple as a list of words. Here, we did a large-scale simulation of language model effect, assuming certain user behavior. The user behavior is what I described earlier. That is, they do tab keys with essentially follows a Gaussian distribution, a generic Gaussian distribution. So we use such a kind of simulated human user and apply such a user statistically onto typing a large amount of text. In this case, the text is all the words typed in the unrun corpus. It's a whole company that got forced to publish their email history due to litigation. And that became a gold mine for NLP and many other domains. So we trained a general language model from the web, scrapped and normalized and cleaned up. We did smoothing on it, and we did entropy pruning so that it could come down to a manageable number of n-grams. And with a set of a fairly respectable language vocabulary size, 168,000 words. We also did personalization, which is an important aspect we want to study. That is, if the language model is personalized according to your own use history, and give a bias to words you use often, would that help? The intuition helps, but it can also be having negative consequences too, because the bias towards recency, and sometimes you want to switch topic. You want to talk about other things that you haven't talked about. If you don't have a language model, you just apply the Gaussian distribution that we collected empirically based on the early work we cited here. Then you actually have about 40% of words that are actually wrong. Often people suggest, oh, why don't you turn off the autocorrection? Because the autocorrection is bothering. But the bothering is when you type a word that is not in the vocabulary. But when it's in vocabulary, you actually typed it wrong. It actually helps to get corrected. Usually people don't realize that. And there's a very general phenomenon of artificial intelligence or machine intelligence-based user interface. That is, when it helps the user don't realize and don't necessarily appreciate. But when it hurts the user, they really hate you. So there's a whole website mostly dedicated to iPhone keyboard called Damn You Autocorrection. And actually, there's a book written about it. But if we personalize it, it may help that a little bit better. So again, without a language model or decoding, it's about 40% of errors, 38 in this test case. But once you apply a language model, even if it's a generic language model, it reduced to about 6% of the words that are wrong. Still a number that is too high to our liking, but it's much, much better than 40%. Then if you apply personalization, that has another about 10% relative error reduction, another about 1% absolute reduction. This personalization simply means a cache model trained on the 30 days of the user's email and blend that language model with the base model on certain alpha value, lambda value, somewhat arbitrary, that was also optimized for the data set. We thought a decay model may help better. That is, more recent data would help more than more distant data. And we didn't show any advantage in this case. In fact, people tend to repeat words, but when you are really short, you actually don't want to repeat that. So for example, it's almost true in all languages that you don't use same words twice in the same language, in the same sentence. So when it comes to 10 or less than 10, the probability of reoccurring of the same word actually decreases. It peaks about 10th words. It's the most likely you mention the same word again. There's that phenomena. But most importantly, it's because the n-gram models actually alone isn't enough if you don't take other context into account, like whom you're writing to, if you're writing a new email or same email, or same paragraph, different paragraph, this all may matter. And that's not considered in this simple language model. But having said that, when we do apply these techniques, it's often also not straightforward. So back to spatial model. I talked a little bit about tapping keyboard. I also talked earlier about shape writing, that is gesture-based keyboard. So what is the model, the spatial distribution of a gesture given a word? And that required new knowledge to model. So here we developed a model fairly recently generating keystrokes, gesture strokes for given words, any given words, arbitrary words, that would mimic what a user would produce. This model is based on a fairly well-known phenomena in human motor control called a minimum jerk. That is, all things considered, the user or the human is most likely making a movement that minimizes the third order derivative of the movement. That is, first being velocity, and the second order being acceleration, and third being jerk. So it has an effect that it smooths the trajectory, but also minimize energy expenditure. So according to that model, this is a set of gestures we can produce. For example, this is the word then, and then the word then 3 times. You would have different gestures because it's a statistical model, essentially sampling these via points from like a Gaussian distribution on each anchor point or via point, and then the energy minimization is on the or jerk minimization is on the total gesture. So we see different phenomena. So once we have these kind of model, we can use the model to say train LSTM model or some other neural net model as a way of, in shortage of real data, gesture data, to train them on a neural network model for error correction. This is probably the first paper that uses deep neural net to represent a user spatial model in a keyboard. This is experimental research. The other aspects of keyboard design is that how well the model can scale spatially, because we use devices in all forms, in all sizes. And today, phones getting are much bigger than old phones. And there's general tendency of getting bigger phones. So from those bigger phones to also much smaller watch relative to the finger size. So on a watch, the finger is covers about 3 or even more letters on a watch. So the question is that whether the same decoding technology would still apply and can still work on a watch form factor. And we did this experiment. We ported the code to a watch. In fact, the same code in terms of decoding as far as decoding is concerned. And we look at the empirical results, and we were quite surprised ourselves that it's actually possible to scale the technology to such a small form factor. Other colleagues in the HCI field had thought it was impossible. So they started inventing ways of dealing with very small screens by essentially breaking down each letter input into multiple actions. Let's say you tap the keyboard, the keyboard will zoom up. You tap the second time, it will give you a key. Or you shift the keyboard around at the first stroke, and you tap a keyboard. Tap an individual key that is only portions of the keyboard. Therefore, you can solve the precision problem. But here, we demonstrate when we use this machine intelligence-based method, from the get-go, we can reach like 20 words per minute, twice as much as the traditional HCI techniques without using machine intelligence. And here is a demo on a phone, on a watch.
We present WatchWriter, a finger-operated keyboard that supports both touch and gesture typing with statistical decoding on a smartwatch. Just like on modern smartphones, users type 1 letter per tap or 1 word per gesture stroke on WatchWriter, but in a much smaller spatial scale. WatchWriter demonstrates that the combination of human motor control adaptability with modern statistical decoding and error correction technologies developed for smartphones can enable a surprisingly effective typing experience despite the small watch size.
So that even surprised us. We thought, well, it may be possible, but I didn't know it will actually work so well. It actually worked so well that we actually launched this product in Android Wear or Android Watch devices about a year ago. So earlier, if you remember the video I showed, we were initially demoing or developing the technology on a new layout called Atomic. Atomic was, as I said earlier, was optimized for minimizing distance. It's not necessarily good for gesture typing where the distance matters, but more important is that the keyboard should separate the word shapes into as diverse a set as possible. It should minimize the chance of collision. Partly because of that, and partly because users are already familiar with QWERTY keyboard, so when it comes to actual product, they were actually deployed on QWERTY keyboard. The initial ShapeWriter product on iPhone actually did have an option on Atomic, and some people wrote to us saying how much they loved Atomic, but nonetheless, it didn't take off. So this vision of using shape as the primary modality of encoding words, I would say still is a vision to be achieved. So lately, we have been returning to this topic, say, provided we can move keys around and find a way to get user to learn it, what's that layout? What's that keyboard? So here is a paper we published a few years ago, motivated by that observation. The first key layout here is QWERTY, of course. And you can see the word QWERTY here. I guess we're trying to write the word OR versus OUR. Or, the word or our. On QWERTY, exactly same shape, same location on QWERTY. O to R versus O to U to R, exactly the same, no difference. On a new layout, this layout, it gets separated. On another layout, it gets separated. And this layout all have different objectives. And here's a multiple objective optimization result. This dot cloud represents 3 object functions separately. One is speed, is how fast you can draw this gesture. One is clarity, that is the statistical probability, a statistical chance for 2 words to collide. And the third dimension is we design in such a way it's similar to QWERTY, because we believed that the more similar your result is to QWERTY, the faster people will learn it, because people are already familiar with QWERTY keyboard. So this dimension, each dimension got normalized to from 0 to 1 to the best possible on a 3x10 grid of keyboard, which is actually also not very good for shape writing. But given that, we find this so-called Pareto front, so that we can find the best compromise on all 3 dimensions. And that's still ongoing work, because each time we find something, it seems to be good in one dimension, but it's not so good on the other dimension. So we are still, especially when it comes to learning, we come to realize that a simple change, like if you swap the key I with J, it actually helps about 10% on clarity. Because one of the most obvious drawbacks for QWERTY, even for tapping, in fact, is I U, O are all on the top right corner of QWERTY. So if you write the word tip or top, or in this case OR and OUR, you all travel to the same corner and they all give you similar or exactly the same shapes. If you just sweep I key away with J on the second row, and all of a sudden you can avoid a lot of these collisions, about 10% less. But nonetheless, when we did that, we find that's just not enough of a gain in terms of performance, but also still at some cost to human familiarity. It took me a week to get used to it, so I thought it was too long. So we're still working on this, and it's still open topic. That is, how do you find the optimal layout, and how do we get people to learn a new layout? These are still open questions. I'm mostly spending time on talking about technologies that would automatically correct users' sloppy input. And user sloppy input is just human nature. And also, the better the technology gets, the sloppier they will get. And that's actually rational because they are playing a speed accuracy trade-off. The more error you allow the users to make, the faster they can do it. It's also, they will express less information, and hoping the language model or the machine intelligence will pick up the slack and fill in the missing information. And it's also fundamentally due to the fact that language has a great deal of information redundancy. If you look at the original paper of Shannon, the first many pages was spent on this redundancy in terms of, or regularity in language distribution, letter distribution, that partly motivated, inspired Shannon to go on to for his noisy channel based information theory development. But another aspect of language model or machine intelligence that can do is to actually make predictions, so that you don't have to enter the entire word. You can just type the first two or three letters, the word or even the next word gets predicted. And in fact, one of the most popular features that Google developed in the last few years is called Smart Reply. That is, you don't have to type anything. You look at the email you received and ultimately compose a short answer. Sometimes they will hit it, and sometimes doesn't. But it comes down to how much it hurts when it doesn't predict what you want to write. And this is the paper looking at a simpler case. That is, if you complete the user's word before you tap the letters, how much perceptual, cognitive, and motor cost there is. You have to overcome that cost. So let's say we make 3 predictions for typing the word here. So I typed SUB in here. Let's say I typed SUB in here. And the system predict suburb, subject, and subway. And one of them might be what you want. So this experiment emulate about the best possible language model prediction, which gives about 40% keystroke savings, and sits on average, and see how much cost there is to take the rest of the saving on a keystroke level. So fundamentally, we want to assess the utility of the suggestion. So the cost side comes to a few things. One is that you have to look at the suggestion bar. And the other is that you have to make a decision if the target is in the multiple presentations, multiple candidates. And if it is, you have to click on it. So there are 3 costs associated, at least 3 costs associated with taking a suggestion, if it's there. There's also some uncertainty cost that it may not be there at all. We also manipulate other dimensions in terms of how aggressive the system should speak a suggestion, or how introverted it should be. That is, when it's not confident, it doesn't do it at all. So all these were factored in. And we studied the actual empirical test. It shows that actually a lot of the suggestions offered weren't taken, and sometimes they were taken by the real user. Overall, unless you do very, very long span prediction, let's say I say how, and you type how are you doing, and you take the whole thing, that's a lot of savings that would be worthwhile. And a lot of times, if you just give a few letters, like say, I typed TH, you say, oh, you want to TH E, that's pure cost, because taking the letter E is just as well as suggestion E is just as long as typing another letter E in terms of the number of actions. So we did this calculation, so it really depends on how far you can predict and how well you can predict. So I've talked about various aspects of text input, and there's a lot more behind the scene that I won't have time to talk about today. But I would just summarize the current promising directions of text input, or HCI in research in general, is that increasingly we move to computational intelligence, powered by data and deep learning, to give user to either relax the user requirement on the part of the user's action, or by providing long span predictions. But on the other hand, there's both cost and benefit, particularly the uncertainty that is, it's not always guaranteed that the machine prediction will be matching what you need. That uncertainty, that unreliability itself is a huge cost. So if you just 2 or 3 weeks ago, we announced at the Google I/O conference, we announced that the same technology of deep neural net prediction that used for smart reply, now we actually also use the technology in the writing process. So as you write, it may make a very long span predictions called smart compose. But there we just tried very hard to minimize the distraction so that it only predict when it has very high confidence. But this is still a question to be answered by either better technology development, so we reduce the uncertainty, or by understanding when we should predict and when we should not predict. The other is just deeper human factors research that give us more insight about how humans behave, and we can leverage that. And one of the directions, again, is the original vision of shape writing that we'll continue to pursue. So I'll stop here, and I have a lot more slides, but if you happen to ask questions that matches those slides, I'll talk a little bit more about those. Otherwise, I'm open to all questions.
So, thank you for this presentation. I just ask you again, please, if you have a question, since we have about 60 people looking to this conference from home, use this microphone for making your question, okay? So, does anybody have a question?
You explained about the simulated annealing. Earlier you spoke about the simulated annealing method. Earlier you spoke about the simulated annealing method to find a minimum of some kind. Are there other stochastic methods that you use to find this minimum?
In fact, I just came from Helsinki, where I examined in Finnish terms, opposed a PhD defense, which looked at applying more traditional OR techniques, more exact methods for optimization. Certainly there are other methods for optimization, But in our experience, simulated annealing works pretty well for this type of problems. Initially, when we thought of using this, some other colleagues thought it wouldn't work well, but our experience, it works pretty well so far. But it doesn't preclude from other better methods. Especially, we still face, surprisingly, a scale issue. So for example, if you optimize for travel distance, that's only based on letter level transition probability. And that's actually a fairly small configuration space. When we optimize for words, that gets much bigger. So every word, essentially, every step of the optimization, every single step of optimization, you have to consider a targeted word and all rest of words combined. Of course, you have to use pruning techniques as you go. So you don't evaluate every single other distractor. You only evaluate the distractors that is closest to this word drawn. But at the next level, if we want to do complete simulation, it's many orders of magnitude more complex. Let's say if the language model actually has an impact on spatial model. That is, let's say, actually, it really doesn't matter if word OR and OUR collide, because in real use, the context would always sort them out. The two words will never happen in same context. If I'm making an extreme case, then you should not worry about the spatial collision. There are cases like that. If you do that, that means you have to do simulation on the entire corpus, or at least a set of sentences to test that. And that becomes almost still intractable, despite the amount of computing power we have today. So the answer is that we always look for more efficient optimization techniques. But so far, it seems to be working pretty well.
Thank you.
Other question? Yes.
What technology did you use to generate the Pareto front in the multi-objective optimization? Maybe an evolutionary algorithm?
That's the simulated annealing.
Okay.
Yeah, simulated annealing. Yeah, other algorithms can.
Okay.
Yeah,
also, how many objectives did you take into account? 3 or more?
Three.
Okay.
So far, and right now in my own mind, I'm pretty much given up on the third dimension. That is the QWERTY similarity. What we're really going after is learning. And this is actually an open topic we have not solved. And it's not clear whether there's anything that we can take advantage of it. It's something I didn't talk too much about. We have done quite a bit of psychological research on what makes a keyboard easier to learn. It's only 26 keys. For a computer to memorize that is trivial. For us to memorize 26 key positions, surprisingly hard. We thought about top-down learning, that is giving some clues, like the atomic layout, which has certain alphabetical tendency. It actually doesn't help much, if anything at all, because recalling alphabetical sequence itself is a cognitive process that might be too slow. We thought about ideas like you provide landmarks on the keyboard. Let's say we highlight a few keys. And so when it comes to remember keys, you say, oh, that key was a red key, a key next to a red key, just like how we navigate in natural world. We thought that may help, but all these techniques help just a little bit. It's not enough to justify them. So that's still open topic. The most effective technique that helps learning so far is QWERTY. Is that the more similar it is to QWERTY, the faster people will learn. However, QWERTY happens to be bad for shape writing, because the zigzag back and forth means that all shapes or majority of shapes are defined in a very similar way. They always tend to be very similar. Therefore, for technology, for the machine side, it tends to be hard to separate out, hard to classify to 160,000 classes. But But for humans, it's also hard to recall because they don't have enough features. And that's still open topic in terms of what makes learning easier. So far, in my mind, I give up on the QWERTY similarity side. The rest is that how do you combine, or how do you even do, well, it's easy to define actually shape similarity or collation. We'll just use pretty easy to do. It's also somewhat open a question to define object function when it comes to clarity. But we have more or less an operational method to essentially the recognizer itself. So we use the recognizer itself to separate, to say how close they are. We use the recognizer to calculate how close two shapes are. And that's essentially the shape writing algorithm initially defined, which works pretty well. It doesn't consider language model too much as an objective function. For speed, we actually also use a model which I didn't have time to talk about. Let's see if I can find that. This model. We call it CLC model. Basically, all gestures can be broken down into 3 elements: corners for surface C, length or the gesture length, a straight line, or curves. And curves can be modeled by the power law of curvature done by an Italian researcher quite well known in motor control community called power law of curvature. Each of these elements can be modeled into a time cost. And then all gestures can be broken down into these three elements and summed up. Not a very elegant model because initially I thought it was some sort of entropy that would dictate the amount of time. But we didn't find a more graceful formula for that. Instead, we use these component models. And this is still one of the models we use for modeling how long it would take to write a gesture. And we'll leave the error side to collation. That's the current path we're still moving towards.
Another question? I have one, very simple.
Right.
Now multi-finger gesture is being used for rotating, resizing, not for writing. Is there any reason, special reason for the missing of such attempts of using simultaneous multi-finger gestures?
We actually did that. I don't know if we'll have a slide on that on this deck. Maybe not. It's called bi-finger gesturing, because one great advantage of QWERTY keyboard or other keyboard is the alternation, which brings certain parallel actions on the 2 sides. So one hand is down, the other hand is actually already moving towards a neutral position, if not the next key. And that helps a lot. It also sometimes hurts because in traditional typing research, there are different classes of errors. And one class of error is transposition error. That is, you type THE, you end up typing HT because one finger gets ahead of itself. So that is something we wanted to do. That is, you can gesture left and right, only partially. And we did that. The end result is that we actually launched in some early versions of Gboard, a Google keyboard decoder. So if people discover that, they can do that. The result is not great because it does introduce a lot more ambiguity in the sense that one big advantage of gesture typing is one word, one stroke. So often at Google, I see my colleagues in conferences or meetings, they were gesture typing. They do a gesture and then tap on the space bar. And I almost want to tap on the shoulder as well. You don't have to do the space bar because the space comes for free. Because each stroke end is also it's a word segmentation cue. But if we allow gesture type left and right, that means you have to solve that ambiguity. That is, it could be a gesture for one word or a gesture for part of a word. So unless you enforce a user behavior, that is, you don't release your hand if you're writing the same word. So you gesture this, and then gesture on the other side before I lift the other finger. It gets a little bit constraining. Or we use timing signal, so which we did, but the timing signal means that you cannot be too long, and so on and so forth. So the benefit is not as much as we wanted, but it does benefit for if you train yourself to do that. So we don't. It's still another open topic. Yeah.
Okay. Any more questions from? Okay.
Thank you for the talk. Do you think that in the next future there is still be space for typing or swiping, or are these going to be deprecated in favor of, for instance, speech recognition or, I don't know, body language recognition or something similar? Thank you.
Yeah. Gee, I also may have a slide on that. Don't. No, but let's see. Actually, that's a very interesting question. Let's see. Gosh, it's slow. Huh. Probably not. Yeah, actually, I'll show this video, which is a TV commercial of Nexus 7.
Google, what is glossophobia?
Glossophobia, or speech anxiety, is the fear of public speaking.
Resolutely faithful to it.
This is preeminently the time to speak the truth frankly and boldly. This is no unsolvable problem if we face it wisely and courageously. Let me assert my firm belief that the only thing we have to fear is fear itself.
So there you go. It had both speech and gesture typing, and so on and so forth. I was looking for another video. I didn't embed in this slide deck. But yeah, speech technology is getting better and better, and it's quite practical today for essentially search kind of tasks or command kind of tasks. So I worked on another project last year in this phone called Pixel 2, and it has a feature that that makes voice interaction even easier than, say, using OK Google to trigger it. I did trigger this in the case. So so basically, I squeeze the phone and say, "What's the weather?" and it will answer me. The advantage of this is when you have a conversation with it, you don't have to keep on saying. You don't have to say OK Google every time. So this just says 77 degrees in Fahrenheit, and now say, what about in Celsius? I can just click on it without saying OK Google. What about Celsius? So speech works pretty well for assistant and search tasks. It doesn't work nearly as well for typing tasks for many reasons. One of the reasons is quite fundamental. That is, writing gives you an intermediate representation. So your composing task essentially happens on the paper or the screen. So you can sort of wordsmith your sentence along. Sometimes you even change a word to find a better word within the same sentence. But when you do speech dictation, it means that you have to be much more disciplined. You actually have to think of the sentence in your head, and you cannot change in between. Although speech technology is also moving forward. Lately, we use much deeper neural networks to do the decoding. Sometimes actually it can even ignore some words you like hesitated in the sentence along the way. But nonetheless, there are all these challenges that make speech to work in some situations, but not in other situations. Certainly not in social situations. You want to on a bus or in a public space or in a meeting, you don't want to speak, rather you want to type. So there's definitely spaces for both. And certainly there's the video I want to show was actually April Fool's video we made but never released. That is, you can just look at the screen and it will type what you want. It turns out now the technology is called Smart Reply instead.
Thank you. Any other question? So again, I would like to thank Dr. Zhai for his kind presentation.
Thank you. So feel free to write to me if you have other questions or ideas or suggestions. Also, we're constantly looking for talents.
Could you put your email on the screen?
Okay.
If they would like to write.
Do I have it? Oh. Okay. It's my last name, Zhai. Gosh, the screen opens freezing because I did. Do I have it? Here.
Yeah.
Zhai
Okay.
at acm.org. It can be also Zhai at google.com.
Okay.
Either one would work.
Thank you.
Does it show? Yeah. So here's on the screen. I was saying we're constantly looking for talents who want to make user impact at scale. So when you are available and want to work at Google for the world, talk to me. Of course, we have a very stringent interview process, but I believe it's possible.
Google takes in also PhD students for abroad period?
Internships, postdocs sometimes. Okay. But postdocs, there's a formal postdoc program, which is very rare. I've hired postdocs through that channel, but there are other channels to hire postdocs as just a term employee.
So in the case they can contact you.
Yeah, as well. Yeah.
Okay, good. Good to know.
We're currently working on haptics, on input, on keyboard, sensor-based input, or sensor fusion. All these things are of great interest to us.
Good. I also would like to thank the people looking us from home. We have 60 people now, so that's a good number. This concludes the seminar, so thank you again, and see you to the next time.
Okay.
Bye.
Bye-bye. Bye-bye for people on the internet.